All right, so we're talking about magnetos. The key word, or the root word being mag for magnets, and neato for cool. So they're cool magnets. We're also going to talk a lot about magnets when we get into non-destructive testing. So this will count for both. All right, so let me see. This thing goes to sleep. We shall start with magnets. Magnets. Hang on, almost situated. One. Magnets. One. Magnets. So definition. A magnet is an object that attracts ferrous metals. An object that attracts ferrous metals. It produces a magnetic field external to itself that reacts with magnetic substances. So it produces a magnetic field. Magnetic field.
Ask a question.
Yeah.
Ferrous metals.
Oh, good question. Ferrous metals. Ferrous is Fe, ferrous, which is the periodic table for iron. So, what's that? Ironic metals. So, yes. So they are metals that have iron in them. So if it has iron in it, it will be attracted to a magnet. So that means aluminum, no. Copper, no. Stainless steel, yes and no. There's different versions of stainless steel. Not writing it down on the test. Austenitic and martensitic are two of the main ones. The austenitic is not magnetic, and martensitic is. Except when you heat them both to red hot, they both are. Well, the austenitic, you take it and get it red hot, you can pull it up with a magnet, and as it cools, it'll drop off the magnet. You should do that. That's kind of cool. So,
Isn't that opposite of
huh?
iron? Isn't that opposite of iron? Does iron lose its magnetism as you heat it up?
Yeah, if you get to a Curie temperature, it is zero magnetism. Yeah. But I don't know about red hot. I think it's still, maybe, I don't know. Okay, produces a magnetic field external. That was a good question, by the way. Exter, external to itself. That reacts with magnetic substances. I.e., ferrous metals, iron. So let's talk about the magnetic field. The magnetic field. Magnetic field. A magnetic field is an invisible line of force. Invisible. Justice and liberty for all. Lines of force. Sometimes called lines of flux. Thus the term flux capacitor. And now you understand that a flux capacitor would in fact be something that is a capacitor that stores flux for the flux machine. That leaves the North Pole of the magnet and enters the South. I was going to get ahead of myself, but I shan't. but I will tell you this. So when we're talking about magnets, every single magnet's going to have a north pole and a south pole. A north and a south pole. And this would be a bar magnet. That's what we call that. And lines of flux would leave the north pole and enter the south pole. Lines of flux do not cross each other, and they concentrate at the poles. So there'd be lots and lots of these. And we could actually recreate this with some iron filings and a magnet and some paper or some steel. In fact, I've got everything I need to do it across the street. I bring it over here, I'll make a heck of a mess. So we don't want to do that. So in theory, it leaves the north and enters the south. The way I remember that was be thinking about the Earth. And as you just witnessed, the Earth has a molten core. It's a little more molten than the video projected. And within the Earth is thought to be a magnet with a north pole and a south pole. Now here's the hard part. So you have a compass. You have a compass. And of course you've got compasses. They're shaped kind of like a diamond. Well, on one end is usually red, so we'll make that the red. And that red points towards north. Well, and we have learned that opposites attract in this case, and like repels in all cases. So is this piece, so the originally compasses were made with what's called lodestone, which came from the term leading stone, and they ended up calling it lodestone, which is simply just a natural magnet. It's a magnet found in nature. And I don't know, somebody probably was playing a joke and they dropped it in another guy's coffee, and he's like, dude, check it out. It always points that way. And so it became a compass, right? And that's how it worked, as it always points towards north, magnetic north, that is. And so there we go, compass. So if this is north and there's a magnet in the Earth and that's the north, and as I said, the lines of flux come out of the north and come around, and that's how I remember that. They leave the north, which is up, and then fall down and then come back in. So it does that. Then, and opposites attract, does that mean that this is the south end of the lodestone and this is the north end?
Yes. That's a labeling issue.
What's that?
It's a labeling issue.
Or is this really the north end of that, and this is the south end, and this really isn't the north, this is the south, and then this is the north end of the magnet, so that it all works?
Yeah.
Yeah, sure, whatever. Okay. Okay, good. However I want to explain it. Well, then the way I want to explain it and the way I want it to be, and therefore it shall be, because I get to make the rules because I'm standing up here, and because when I go home I don't get to, so that's sorry for you guys. Then I like to think of it like that. And then I like to think of this right here as that was a terrible, terrible arrow. All right. This part right up here is the north seeking. The north, that's a H. North seeking, N-O-R-T-H. North seeking end of the magnet, and then this would be the south seeking down here. So we just get rid of that right there, all that. So there. North seeking and south seeking. Can't argue with that.
If we Google that, we get your picture.
On Wikipedia. Yeah. I should get a Wikipedia page. You just write all kinds of nonsense. All right, so I call that the north seeking. Well, yeah. It's another great Office quote on there. Everybody can go on there and just put whatever they want. How could it not be right? All right, so let me see. This is kind of the sub-point under that. This is purely theoretical and not actually known if there is any movement. So this is purely theoretical. What is purely theoretical? The fact that lines of flux leave the north and fall down and enter the south. Theoretical and not actually known if there is any movement. And, or maybe they do by now. I don't know. We just crashed a spaceship into an asteroid. Who knows what we know? Not actually known if there is any movement. If there is any movement. Magnetic flux is the strongest and most concentrated near the poles. By the way, if you were to break a bar magnet in half, what happens? You get two magnets. You just break it in half, then this becomes the south and that becomes the north. So, what's that?
I just said because now it wants more negative.
Just leave it at that. One becomes south, one is north. Purely, not know there's any movement. What did I say? Magnetic flux is strongest near the poles. I mentioned this already. Flux lines do not intersect. And flux lines take the path of least resistance. What has more resistance, air or steel?
Air.
So air, keep that in mind, air has more resistance than steel. So given its choice, the lines of flux are going to want to go through steel and not so much air. Air is kind of a last resort there. Well, if we look at the bar magnet, it has no choice because it has to get from the north to the south, and there's only one way to do it. Yeah, you'd think, well, why doesn't it just go this way? It's that movement theory. So it kind of like internally goes from south to north and then outside from inside south to north and outside north to south. Not to confuse the thing, but so this is a bar magnet. And technically, when we get into non-destructive testing, we're going to study more that there's two types of magnetism. There's circular and longitudinal. And this right here would be longitudinal magnetization because the north is here and the south is there in a bar. But if I had a circle, if I have something like this, and I've magnetized it, and I've magnetized it such a way that this is north and this is south, and then the magnetic lines of flux have to go like this. And when you get into non-destructive testing, you don't care what north and south is. It's completely irrelevant, and for the most part, it always is. Can't really think of any times where it becomes relevant because it's theoretical which way the lines of flux go anyway, so it doesn't matter. So in circular magnetization, let's see, we would longitudinal. Sorry, I said longitudinal. So longitudinal magnetization, we magnetize it such a way north and south of here, but we can also magnetize it in such a way where instead of longitudinal magnetization, we have circular magnetization, which is really what you would get if you took a bar magnet like that and bent it. Now I'm really going to have to draw them. If we bent that bar magnet around in a tube, that's north and that's south, or either which way, the lines of flux now are contained within it, and you can't really sense it. It can be highly magnetized, but the magnetic lines of flux, now I have to do them black, are just going to traverse right through here. Now, if you take that bar magnet, bring it all the way around into a circle so both ends are touching and actually fused them, then what you get are the lines of flux just travel around inside of it, and you get almost no perceivable leakage whatsoever. Because, like I just said, the lines of flux want to stay within the steel, and they don't really want to go out into the air. Well, since I've already drawn this, and I can tell you that what you get, though, is this little split right there. And that's one of the theory, that's how we do non-destructive testing, is we take a fluid and we put it over something, and we're looking for lines of flux leakage. And you will, in fact, get lines of flux are going to leak out of right here as they travel through the air. And if you put some sort of iron filings across there, they will collect at that spot. And so if it was a tight crack that you couldn't see with your eye, you can sprinkle those iron filings on there, or it could even be subsurface. If you have a subsurface crack, some of them will still leak above the discontinuity, and then you'll get an indication. And that's basically non-destructive testing in a nutshell. So back to magnets.
Can you scroll back up a little bit?
I need to get that little, is it the Jeopardy song? Dun, 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 dun. You good? All right. I don't mind waiting. I really don't. All right. There are different kinds of magnets. I'm not using neon green. All right. We have the permanent magnet. Which, as the name implies, is in theory permanent. Nothing's permanent except for death and taxes. So here we have a permanent magnet out of a magneto. And it'll stay magnetized for many, many, many years. Without the keeper on it, though, it has to kind of work a little bit harder, because the magnetic lines of flux have to leave here and come back around, and that takes some work because air has some resistance. So when we're not using them, we stick them in a keeper, which does two things. One, it would preserve the magnetism of the magnet, in theory. I don't know how true that is, but maybe it's like leaving a battery on the floor. You just do it because if you don't, somebody's going to yell at you, your magnetism's leaking out. So, but the thing that's not really that arguable, it tends to keep the magnetic lines of flux contained, and it doesn't pick up your metal parts quite as readily as it would without it. Make a liar out of me. Yeah.
So it won't cut you.
Eh. In theory, it should keep it to a minimum. Depends on how strong the magnet is. All right, so permanent magnet maintains almost constant magnetism. Maintains almost constant magnetism without the application of a magnetizing force. Without the application of a magnetizing force. However, you have to apply a magnetizing force to magnetize it, then you don't have to afterwards. So it doesn't just like, ooh, look, it's magnet. How to get that way? Well, Kevin said, without the application of magnetizing force. You have to apply the magnetizing force, then remove it, and it stays magnetized. Which, by the way, I've mentioned this to many people, yeah.
What about a naturally occurring magnet?
Well, we'll write that down here a little bit later. That's going to be C. D-E. D, next one. All right, which technically would be a permanent magnet, but I'm talking about it more in the sense of a man-made item. I am demagnetizing your rotors in class. Okay, we don't do that in the field. That is not something that we did in my shop. That's ridiculousness. Why would you decrease the magnetism when we'd have to redo it? We added magnetism. We would just take the rotor out, and then as we were overhauling the magneto, or anytime we took a rotor out, we'd stick it in the machine similar to the one we have here, give it a couple shots, and just charge it back up. You don't decharge it and then recharge it. The only reason why I'm demagnetizing your rotors is because we can, and it's fun. It's just something to do, It's like, hey, look, it's dead, and then you can see how well it recharges it. Otherwise, you'd think I'm lying. It's like, I put it in this machine, hit the button, the guy's full of crap. It's not doing anything. So now you can see what it does. These are very, very hard to kill off. Very hard. I mean, they have some tenacity.
It also makes using the armor press easier.
Yeah, it does. Makes things a lot easier when it's not magnetized, which brings me to the point. I did do a lot of rewriting in your project sheets, and one of the things I should have done is not have you remagnetize the rotor until after you do end play. So try and remember that. Just do end play, get it all done, and then recharge the rotor. Last thing. Okay, A, B, C, D, natural magnet. That is a magnet that's found in nature. So technically, if I drop this somewhere out in the bushes and you find it, it is now a natural magnet. It's called a lodestone. Or leading stone, because explorers used it as a compass. And the third type is the electromagnet. E-L-E-M-A-G. Electromagnet. That's magnetic. Electromagnet. There we go. A magnet made by electricity. So a magnet made by passing current through a coil. Where do we find that? No, we're not going to make an electromagnet out of it. Relays. Yeah, scrap yards with the big crane to pop. We're going to see them in generators. We're going to see them in alternators.
The hadron collider.
Yes. The colitis. What?
The Large Hadron Collider.
Yeah. Sound like you said the colitis. I think that's a colon thing. Sure, I don't know. Suppose if you shove a magnet up your butt, you're going to get colitis. Oops, I gotta edit that part out right there. So left-hand rule. Left-hand rule. Left-hand rule. When a coil is held in the left hand with the fingers pointing in the direction of current flow. Left hand, fingers pointing in the direction of current flow. Thumb will point to north. So now I got to remember if that was, we'll assume that it's electron theory flow. And it's really not that important, so why did I write it? I don't know. I guess just so you know that there is a rule, and it is going to, north is going to depend on which way the current is flowing, which we've already talked about that. So if we said that current entered here and was flowing around this way, and I held it this way, my fingers are pointing in the direction of the current flow, I would say, well, that makes this the north end over here, if this were electromagnet. Left hand rule, let's see, when a coil is held in left hand. When a coil is held in left hand with fingers pointing in direction of current flow, thumb will point to north. And in an electromagnet, the strength of the magnet is directly proportional to the amount of current. In other words, the more current you put through it, stronger the magnet. All right, ends of the magnet, two ends of a magnet. What are those two ends? We'll call it north seeking or north. Yeah, will be the end that points north. Will be. Do I want to write that? No, let's change that. Let's call it. Let's get rid of that. Do something different. Well, because I'm thinking about it from a different perspective. So I take a rotor and I have to label one side of it north and one side of it south. Well, that won't make sense if I write that. The north seeking, aka north, will be the end that points north. Well, no, that would work if this was allowed to line up with, if it was a compass, that would work. But I'm not talking about a compass, I'm talking about something like this. So by two ends of the magnet, I would say, let's do this. We'd have the north end. That would draw a compass needle to north. Does that work for you? Causes compass north to point at point at it. I don't know.
Would that be the south?
South, yes.
Not the way we have it set up in lab, right? Am I right about that?
Oh, because the compass, the north pointing end is really the south end of the magnet.
Yes.
Yeah, okay.
So if you're going to label, this is a little, as I said, this is weird. So what I had to do with this is I had to reverse engineer all the way back and then write the directions going forward because it gets so confusing. So in lab, we have this, the charger that charges these magnets, right? And on this, it's labeled for a battery, and it has a big plus stamped in it, a big minus stamped in it. So with the battery, the minus goes to the negative, and the positive goes to the positive. Then it has these giant coils, and they're that big around. There's two of them. And they're stamped in them. You can't change it, you can't move it. One has got a huge N stamped in it, and the other one's got a huge S stamped in it. Stands for? Right, so I took a magnet, demagnetized it, hooked the machine up correctly, I put it in there, zapped it a couple times, and then I took it and I said, okay, this is the part that was in the inside of it, and I held it up to a compass, and the compass north pointed right at it. So that means that's north, and the compass has the north-seeking part of it, so that, without sounding confusing, so yeah, the north-seeking went to the north, and then I turned it around, it swung this way in the south, so there we go. So the north end of the magnet, the compass north will point toward that. Yeah.
So what happens, like, when you recharge that magnet? What happens if you flip it around and turn it again? Does it come
Oh,
back?
like you put it in and you hit the button and it was north-south,
And then
you turn it out and you go, oh, just put it, turn it around, see what happens. It'll repolarize it.
Okay.
So it's a little more complicated because you have to consider the hysteresis loop of the metal. Sorry you asked. And the hysteresis loop of the metal will tell you just how far it's going to go the other way. So it might not necessarily, you have to do it a couple of times. Do it a couple of times, it'll be fine. It just pulls it over that way. So, and then the south end of the magnet causes compass south to point toward it. Now, before you do this test and you get a compass out to check it, always make sure the compass is pointing in the right direction. North is that way. And so, because there's a little compass that we put on that little black board that you guys will see, and for many years, it was backwards. South, it always point north is that way. And so, and then for some reason we went out for COVID and we came back and now it points north. Yeah.
The causes compass north to point toward it, causes compass south. Could you also say it tracks the whatever side of the compass?
Say it again.
Where you have written causes compass and
South to point toward it.
So
Yeah.
could you also say that it tracks that side of the compass?
Yes. Yes. Or yeah, it tracks the south-seeking end. It might have been nicer to say. Tracks the north-seeking end.
It would have been nicer to say there are two ends of the magnet. North and south. Moving on.
Moving on. But I can't. So I was talking with Phil about airports and runways, and he goes, "You know you're old when, because you know runways, the number of a runway is the magnetic direction of the runway." And so, geez, I haven't flown in a month. What do we have? We have 1.6 and 3.4?
Yes.
1.6 and 3.4, which is 160 and 3.40. And Phil talks about, I remember when it wasn't that. It was, 1.8 and 3.2 or something. I'm like, what? Well, yeah, the magnetic, we have a variation in our magnetic lines of flux around the Earth, and compass doesn't really point towards north, it points towards magnetic north. And that is moving. And so as that moves and the compass moves, they have to keep changing the numbers of the runway. And so you can tell your age by how many times they've had to repaint the numbers of the runways. Like, whoa. Things you don't think about. Like rings on a tree. Rings on a log. Let's see. Nope, not writing this.
Thank you.
I think we're good. I'll tell you what I wrote so you can. The Earth has a magnetic field like a bar magnet. Then it went crazy. Since opposites attract and like repel, the Earth's magnet is actually upside down. South is the north, north is the south. Nope, not doing it. Earth's magnet is also not aligned with true north. It's magnetic variation, not relevant to what we're talking about. So that's going to put me off once. We'll just put G. We'll put nonsense. All right. So had some nonsense going in there about the Earth, and then A, B, C, D, E, F, G, H. Okay, got it. Theory. All right, it's believed that. So, what is this magnetic field? Where do we get magnetic fields? There's kind of two theories, but you can sort of merge them into one, and it all kind of works out. So it's believed that atoms have a magnetic field. So I find this one hard to believe. So that atoms have a magnetic field, and then and the electrons randomly orbit in there. And because these electrons have a magnetic field and they're randomly orbiting, then their magnetic field cancels each other out. But if you were to take and magnetize the metal, somehow you get the electrons to orbit in sort of the same direction, causing a magnetic field, which I kind of go, well, I'm not really a physicist in any shape or form. And I kind of go, I have a hard time believing that because they're kind of all doing the same thing. But I like the domain theory. And this one is one that I've always worked with, is that inside of any particular bar magnet or any sort of magnet, within it, you have a bunch of little magnets that are just kind of randomly in there as part of their molecular structure. And they just kind of, just put a bunch of these in here. And they're random. So, this is north, south, south, north, north, south, south, north, north, south. And they're all random, so this is a non-magnetized piece of metal. But when you apply a magnetic force to something like this, then all of the magnets inside line up. And when they all line up, you end up with norths at one end, end up with souths at the other, and that causes the part to be magnetized, which I like that. That's the domain theory. So.
But
There we go. So now we got to magnetize it. And then to demagnetize it, all we have to do is scramble the little domains. And we scramble them back up to where they were before, and you lose your magnetism. And the way I demagnetize your rotors is I will put it into the machine, if you haven't seen it, and I will either use the coil or these contact pads, and I'm going to run 2,000 amps of alternating current through it that's switching fireworks.
We're used in early.
They're over. And that will, the alternating current going back and forth and diminishing scrambles the domains in there. In fact, if you see me use the coil, I'll actually hold it in there and I'll twist it quite a bit while I'm doing it. So by moving this and scrambling this at the same time, it's got an AC current that's diminishing over time. It really will deaden these things up pretty good. Reasonably well. You are welcome to put your head in the machine if you so desire and see what that does.
That's a lot of paperwork.
I do it all the time. You'll see, I take my watch off, but my analog watch, I got it stuck in there one time, and I looked at it, and it spun backwards like really fast. I'm like, that's probably not good for it.
That's fine.
So this equipment's pretty new, so I worked hard to get that. So for the first several years I worked here, we had some very old equipment. Like you guys might have saw it. I think it's finally gone from the front. But we had a coil, a standalone coil that was like this big, that we would use for demagnetizing. It was reasonably weak. It didn't work that great. You have a little table and you go back and forth in there. And we were doing some work like that. And one of my students, he's a young kid, but he was insulin dependent. He had an insulin pump. And like he was like all working out. I'm like, dude, your insulin pump's inside that thing. He's like, oh crap.
Was that red one that used to be there?
Yeah, that was the magnetizing one. That was the old. That was the old bench.
Okay.
And then there's, I don't know what happened to that guy. He never showed up after that. But.
Dead.
I don't know what happened.
I think he died in his car out in the parking lot that day.
It was all Kansas, so we don't say there's a death here.
Yeah. Nah, he's a really good, really smart kid. Good instructor, or a good student. So I'll write this. But you know what? Instead of writing it right now, because it's 9:17, we'll just like save that for tomorrow.